My name is Bruce Ballack. I'm the chair of the Astronomy Department. This talk tonight is co-scheduled by the Astronomy Department and the UW Alumni Association. Introducing Don is a very special pleasure. He's an outstanding scientist, a member of the National Academy of Sciences, and the principal investigator, that is the project scientist, basically, for the Stardust mission about which you've come here to learn. Don has a long list of plaudits. His labs are here at UW, at the Lunar Science Institute, at Caltech. He's been working throughout his career on interstellar dust, interplanetary dust, comets, meteorites, and most of all, these things all come together in trying to understand the origin of the solar system. Asteroid 3259 Brownlee is named for Don. He's a holder of the Lawrence Smith Medal from the National Academy of Sciences, the Leonard Medal from the Meteorological Society, the NASA Medal for Exceptional Scientific Achievement. It's an honor to have known Don throughout both of our professional careers. We both came to UW at about the same time. We've been colleagues and good friends, and that extends to our families and, of course, all the rest of the astronomy department. For the past 30 years. Don is one of the more iconoclastic members of the faculty. His interest in dust just never stops. You'll find him crawling along in corners. He asked me tonight to ask you to save everything from your dustpan and to send it to him here at UW. It is my great honor and good fortune to introduce Don Brownlee.
Thank you, Bruce. I'm here to talk about an interesting 10-year adventure, a scientific and engineering adventure called Project Stardust. And this was a joint venture between the University of Washington and Jet Propulsion Lab in Pasadena and Lockheed Martin in Denver. This mission actually had a very simple goal. Go to a comet, grab a piece of it, and bring it home. And this is the first solid sample return mission from space since Apollo 17 in 1972. It's been a long time. But this was a special sample return. We didn't go to the moon. We effectively went out here. This is a view, artist. Actually, it's not an artist conception. I did it, so it's a, it's a cartoon. Anyway, this is kind of what you can imagine the early solar system looked like when it was forming 4.5 billion years ago. And it was a disk with the sun would form in the middle. It had these little purple jets going out the top and the bottom. If you have any questions about that, ask Bruce Ballack. He's an expert on those. I just drew them in because they did exist and they're kind of interesting. But you can see on this diagram here, there's Jupiter marked way in close to the center. The Earth is 5 times closer to the sun than Jupiter is. And this comet that we sampled with Stardust formed out by Pluto, way out at the edge of this disk, out what's called the Kuiper belt, or sometimes pronounced Kuiper belt. It's way at the very, very edge of the solar system. So we went to a comet. We didn't go out to the edge of the solar system. We went out halfway to Jupiter. Actually, we did it 3 times. But we met a comet that was coming in from the outer regions of the solar system. And it's very exciting because this is the most distant thing in the solar system that we can sample. So we did this mission to collect the actual building blocks of the solar system that were preserved at the most distant parts and the coldest parts of the solar system. So what are comets? Comets are, how many comets are there in the solar system? Believe it or not, there are over 1 trillion comets. So if you just start counting up bodies, there are many more comets than there are planets or even asteroids. But they're very far away, and you can't see them most of the time. We normally only see them when they come in close to the sun. So in this picture, you'll see 3 comets. The one on the right is Hale-Bopp. The one in the middle is Comet Donati over Paris in the early 1800s, before the invention of the light bulb. You notice that the city of light is dark, which is good. That was a good time for astronomers. We didn't have to fight city lights. Anyway, an interesting thing about comets is that most people that have lived on Earth over the past 100,000 years have had a chance in their lifetime to see a pretty interesting comet in the sky. They don't hear it very often, but in a typical lifetime, there are a couple of good ones. There have been a bunch of good ones the last couple of decades. Hale-Bopp was a really spectacular one. Anyway, this is the view of comets. And viewed at Earth, you can see a size scale of some tens of thousands of kilometers, a few Earth-size special resolution. But another thing to think about, all these pictures like this you see of comets. If you look up comet on Google or comet on astronomy textbook, let's say this is a comet. Well, remember, when you look at a picture of a comet like that, you're actually not seeing the comet at all. The comet is a black ball of rock and ice. And what you're seeing here is the tail and coma and head caused by the comet coming apart. An analogy I like to give is, you're driving home from work one night and you're like 5 miles from home and you see this huge cloud of smoke off in the distance. That's your house burning up. And you say, there's my house. Well, it's not your house. It's what your house was made out of before it burned up. You normally can't see your house from 5 miles away driving on the freeway, but you can easily see it if it's burning up because you take the house and you convert it to very, very fine smoke particles. So when you see these so-called comets in the textbook, you're really looking at the smoke, the debris from a comet that came in close to the sun. Most comets are far from the sun. They're not very active. When they do drift in close to the sun, the solar heating starts making them come apart. It produces great tails. The tails can stretch more than the distance between the Earth and the sun and make them quite spectacular objects. In really great cases, the tail can stretch halfway across the sky. That's maybe once every 2 or 3 lifetimes, every 2 lifetimes maybe. Anyway, this has been the traditional view of comets. Now, this is the new view of comets that's been around for about 90 days now. On the left is the traditional view. This is Comet Donati over Paris in the 1800s. The thing that looks like a rug in the background is a piece of the comet we went to, Comet Bill 2, at atomic resolution. The picture of what you're seeing there is the rows the periodic rows of atoms lined up in the crystalline olivine from this comet at atomic resolution. The distance between those lines is 2.6 angstroms. Science can make phenomenal strides using technology. This picture of comet on the right is 10 to the 17th, one with 17 zeros behind it, times higher resolution than the 1800 picture drawing on the left. It's not a picture, they didn't have photography in those days. So this is a tremendous advance. And the reason we did the sample return mission is the records that are recorded in that comet that tell us about what the conditions were like in the early solar system and how the comets formed and how the solar system formed are written in these very tiny grains contained in the rock. If you look at it from afar, you're looking at something that looks like a charcoal briquette. An analogy you can think of is taking a compact disc. You can have all your family history written on the compact disc going back thousands of years. And yet, in order to read it, you have to have a gizmo that can look at the information at the scale it's recorded, which is at tiny, tiny submicron level. If you just look at the compact disc and spin around, even look with a pair of binoculars, it's just kind of a little rainbow kind of thing. You'd say, well, it's round, there's a hole in it, and it's real thin, and it's kind of neat. But the information there is uninterpretable. It's like it's coded. You have to look at it at atomic scale resolution. So that's really why we did the sample return mission. And you can do lots of things with samples that you cannot do with spacecraft. This is just a list of them. I won't go through this list, but the science is done mostly on Earth by laboratories all over the world. There are now 200 people all around the world working on the samples that we brought back from the comet on January 15th of this year. And they're using techniques that you would never dream of trying to do on a spacecraft. In a little while, I'll show you a picture of one of the instruments as larger than a shopping center, larger than Northgate up here. Whereas most instruments on spacecraft are pretty small and they have tremendous restrictions of of weight and power and also cost. Even though spacecraft instruments are expensive, there's still limits on cost. If the instrument's on the ground, there actually isn't a limit on cost as long as someone is going to buy it. So if an instrument costs $300 million, which some of them do, we didn't have to pay for it. Someone else built it for something else, and it just happens to be useful for analyzing cometary samples. So anyway, comet sample analysis is extremely important. This is beautifully proven by the Apollo program, where we learned so much about the moon from return samples. So here's our spacecraft. It's about the size of a desk, as you'll see in the next picture. And its primary function is to fly that collector on top, which looks like a big tennis racket, past the comet and collect samples and bring it home. The collector is basically like a tennis racket with a bunch of ice cubes stuck on the surface. It's an array of ice cubes. The ice cubes are the collector material. It's, of course, not made out of ice. It's made out of a glass material called Aerogel, which is a SiO2, silicon dioxide glass, which has about the density of a few times denser than air. It's a very exotic material. I'll show you a picture of it very shortly. So the main function of the spacecraft is to get as close to the comet as we could get without getting killed by hitting rocks, and that's a whole other story right there. But to collect enough particles to analyze and then come home. So the main function, to flip up that fly swatter. As we flew by, we went by as close as we could, collected the particles, and then came home. Now this little spacecraft, in doing this, flew further than any object from Earth has ever gone and come back. It went almost 3 billion miles over a 7-year period. That's about 7 cents a mile. And as one of my team members pointed out, this is the worst possible trip from Florida to Utah. So here's the spacecraft. You see it's a human-sized spacecraft. The part on the top is the sample return capsule. That's what actually came back to Earth in January. The rest of the spacecraft is still in space. In fact, it will come back to Earth in 3 years, and there's at least a proposal to redirect it to fly out to another comet. The sample collector is gone, but we still have a functioning camera and some other instruments, so you can do some interesting science with it. There are some homegrown products here. The big white circle on the left is the high-gain antenna used to send back pictures, and that's made by Boeing. And the 4 sets of thrusters, 16 little rocket engines, which are little, almost finger-sized rocket engines that fired hundreds of thousands of times quite successfully during the mission, those are made by Aerogel over in Redmond. They actually make most of the thrusters for a spacecraft of this type, flown in the United States and also in other places. So it's a remarkable spacecraft. It had to operate all on its own with some help from the ground for 7 years and almost 3 billion miles. So here's the collector. This is the fly swatter that sticks out in the stream of debris coming off the comet. And here's the material we use for collecting. These are the ice cubes that we're filling the ice cube tray in this fly swatter arrangement. And it's silicon dioxide. It's a glass. It's only 3 times denser than air. And it has this remarkable property that when particles hit it, they bury in and stop. The concept here is exactly like when the police want to recover a bullet from a rifle or a pistol. They take a box full of cotton, shoot the bullet into it, and recover it. It's exactly the same principle, except here we're using this exotic material called Aerogel. We actually got a Guinness Book of World Records for developing the lowest density solid here. There are also many other superlative properties of this material. It's the world's best thermal insulator. In fact, our Aerogel is used to thermally insulate some of the rovers on Mars. And it has the lowest speed of sound and the highest range of densities. It has marvelous things. We didn't invent Aerogel. Aerogel was invented at the College Pacific in 1933 in California. It's one of the most exotic materials that hasn't had widespread commercial application yet. It's wonderful stuff, but it's great for trapping small particles. The aerogel that we made, the reason it works is because the solid parts, the solid pieces of glass in it are very small. It's microporous. And the solid pieces are only like 30 angstroms in diameter. So when the particle goes into it, it's kind of like interacting with a solid and kind of like interacting with a gas. It's an unusual nanophase material. So here's the spacecraft sitting on the rocket at Cape Canaveral just before launch. And here's the little launch. We had a beautiful day. A bunch of friends here in the department. We're down there for the launch.
This is the formation of our solar
This is looking down the rocket. And on the left, you'll see a little square with a dot in it. That's where the first U.S. satellite was launched, Explorer 1. And Alan Shepard, the first U.S. astronaut, was launched just next to that dot. That's the Banana River in the background there. There's the 4 solids going off there. Now the first stage comes off. And then see the fairing, the cover that covers the spacecraft, you can see on the left there, starts falling off.
Generator oscillations are damping out. Chamber pressure looks good.
Also, you look on the tower, which says Delta in the Stardust. On the lower left, it says U of W. So, so just for fun, I threw in this. This is not the rocket. This is one of those solids. The solid rocket, there were 4 of those. And that gives you a feeling for scale of how big that is. Those cost about $2 million a piece if you want to buy one. It'd be great to have. Hardly anything beats a rocket launch. There's only one thing that beats a rocket launch, I think, and that's when it comes back successfully. So we did 3 loops around the sun. We launched in an elliptical orbit, and then 2 years after launch, we came back and flew past the Earth, used the gravitational kick from that to go into a larger orbit, which we did 2 times. And on the 3rd loop, we flew past the Comet, which is the largest orbit here, called Wild 2. It looked like Wild 2. And then we came back and encountered the Earth one more time. The spacecraft is still in space, and 3 years from now, it's going to come back and encounter the Earth again. The spacecraft will either hit a planet or go into the sun, but most likely the remaining spacecraft will go off into the galaxy. It'll have a close encounter with Jupiter. It'll go out there in billions of years from now, when we're gone and Seattle is gone and the Earth is different than it is now. That spacecraft will still be floating around there. Now, hopefully there's some people in the audience here that have signed up. This is an uncrewed vehicle, sort of, but we also have a crew of almost 1.4 million people that signed up on the web and have their names engraved in little silicon chips, one of which is still in spacecraft, and the other copy was on the capsule, which came back on January 15. So this is the path we went in space. In the next slide, I'm going to show it has to do with robotic spacecraft. I was talking about crews. This is called a robotic spacecraft. People say robotic spacecraft. Don't believe it. This is a robotic spacecraft in the sense that it can do wonderful things. And there are times when it's so far away from Earth, the light travel time to it and back is over an hour. So if we send up a command saying roll left, and it says Roger, it's an hour. And so it's robotic in that sense, and it also has phenomenal fault protection. You know, if it feels like it's not feeling well, it'll do certain kinds of things. And it is very smart. But nonetheless, it has a tremendous amount of human interaction. The next slide shows the first loop around the sun. Each one of these things here, which you probably can't read from back there, is an event. And during the first year, some of these were anomalies. EJA up there, just a little after launch, that's Earth gravity. Well, that's 2 years. That's Earth gravity assist. A little thing called SSPA anomaly. That's solid state power amplifier anomaly. That's the transmitter. An anomaly. That means this, and it said, and the other things say safing. Safing means the spacecraft thinks it's in trouble, or is in trouble, and goes into a mode where it takes care of itself. It points its solar cells to the sun and doesn't necessarily communicate with us until we command it to. Anyway, there were a number of, if you look around in here, there are quite a few safing episodes, which all provide terror for the ground crew. These are called character building exercises. But it really is sickening because when ET, normally we don't communicate with it. We only communicate in cruise like once a week. And when ET doesn't phone home, you don't know. I mean, there are all kinds of millions of things that could have gone wrong. But one of the most exciting ones was this one. ET didn't phone home after November 8th, 2000 because of this solar flare. This is a picture of the sun viewed with a spacecraft called the SOHO spacecraft. And the sun is actually blocked out, and these are solar flare coming out. And after the solar flare, you saw this look like snow or hen scratching in the background. Those are protons from the sun, high-energy protons from the sun, hitting the CCD, the camera detector, producing scratchy marks, if you will. Now, the way this spacecraft is 3-axis stabilized, it sits there floating in one position in space. It keeps its solar panels, which is its energy source, pointing towards the sun, and it needs to know where it's going. And the way it does that, it's an amateur astronomer. It has 2 star cameras, and it just looks at the sky, and it memorizes the sky very well. So with just one little click of sight of the sky, it knows exactly where it's pointing. It's really a neat trick, except when something like this happens, because there are all kinds of stars it didn't recognize. Normally it sees like 6 or 7 stars. Now there are more stars it doesn't recognize, so it doesn't know where it's pointing. So the camera failed. So it switched to the other camera. It was just back and forth. Actually, it switched complete sides, complete redundant electronic system, side A and side B. It went back and forth several times, and then went into sort of what we call a kind of a death spiral. It was slowly rotating around at 1 revolution per hour, which it would have done forever if we hadn't figured out what had gone on and sent a command for it to wake up. Anyway, it was fine. It just terrorized us for a couple of days. We also, 2 years after launch, we flew past Earth, and this is an amateur astronomer's picture of the spacecraft. Those are dots or stars in the background. A nice aspect of this is we never have to worry about Fox News sometime in the future saying that we faked the mission like they did Apollo. Apparently, a sizable fraction of kids think that Apollo was a fake because people at Fox News ran this trashy TV program sometime in the past. Well, don't believe it, kids. Anyway, we also flew past an asteroid with a famous name, Anne Frank. Asteroids can be named by the discoverer. So this discoverer decided to name it Anne Frank. And we did this as a full dress rehearsal, which is an interesting story because NASA did not want us to do this because we hadn't said we were going to do it. And so we had to use our own money to do it, and it's fairly expensive to do this. But after we did it, people thought this is a really great idea. Every mission should do this if they can. The reason you do the dress rehearsal, just like a wedding, you want to make sure everything is right. So you tell the spacecraft to turn left, you want to make sure it doesn't turn right by mistake if someone got the wires crossed or whatever. And there are lots of non-trivial things that go on. So we did this, and we felt a lot better fly past the comet after we'd already gone past an asteroid. So in January 2004, January 2nd, the day after the Rose Parade in Pasadena, we flew past the comet. This is quite a thing. The body that we saw was just truly phenomenal. We had expected rather a bland object, about 4.5 kilometers in diameter, which is its diameter, and with like 1 jet of gas squirting out. We saw dozens of jets of gas you can see spewing out into space there. We saw a fantastically convoluted surface that's much different and much more complicated than the surfaces of the other 3 comets that have been imaged by spacecraft. It's also totally different than any asteroid that's been imaged by spacecraft. And it's also quite different than the surface of any moon body. So for reasons unknown, it's quite a dramatically different object. This comet has only been in its present orbit since 1974. It did a close flyby of Jupiter at that time and got trapped into its present small orbit, which takes it basically from the orbit of Jupiter to the orbit of Mars. Before 1974, it was in an orbit that went from orbit of Jupiter out to past the orbit of Uranus. So you can whip out your stereo glasses, and if we can turn down the house lights here, And you can put the tab on the right-hand side and stare at that till you can see it in 3D. So the big cavity on the lower right, we came up with the Greek term right foot, and that's a joke. And on the left is upper left is left foot. I mean, usually names of features are named after, Greek goddesses or something. But we did name some of the other features more reasonably. But left foot and right foot were at least easy to keep things aligned properly. So this is in 3D, and this is a sort of a view of the comet when we're up closest to it. And these are short exposures, so you can't see the jets going out. Now I'm going to show a series of pictures. It's going to look like the comet's rotating, but it's not. It's just flying. We're flying past it. So the rotation is, like driving past someone standing on the street corner waiting for a bus. As you drive by at high speed, you're looking at different angles. You get a full three-dimensional view of at least half the person or half the comet in this case. So here we go. I hope you can all see it in 3D. Got the tabs on the right. So here's just a sequence of pictures. This big cavity on the lower left is we call Shoemaker Basin. Okay, so here's a close-up of Shoemaker Basin. It's 1.5 kilometers across. And we would have thought normally this was kind of like an impact feature, but it has this huge pillar sitting up in the middle of it. It's like a pinnacle sitting up in the middle that's several hundred meters high. The sun is on the right, and that pillar is in the middle, and you can see its shadow on the cliff on the left behind it. And you can also see in the upper right, you can see a mesa, a flat-top mountain with vertical cliffs around it, a big blocky-shaped mountain. And then on the perimeter, on the lower left, you can see another mesa, flat-top mountain with vertical cliffs on the side. This is very bizarre material, and it's still actually a mystery to how it formed and why it's so different than other comets that have been seen, other bodies that have been seen. This is left foot, has a flat floor, has vertical cliffs about 150 meters deep, and no rim around the outside. This might be an impact crater, but if it is, it doesn't look like impact craters that have been seen on any other body. It might be a collapse feature, it might be explosion feature. It's quite dramatic. But also, it's amazing to have vertical cliffs. This is right foot, and this is a hard one to view in stereo because the angles between the pictures were so 22 degrees. But in the upper right, there's an overhanging flap that's 200 meters long and 50 meters wide. Now, the acceleration of gravity in the small body is only like 10 to the minus 4, 1/10,000th of a g. So when that thing breaks free, and it will, it's going to take a long time to crash down on the bottom. You could easily run out of the way or jump out of the way if you were there when it fell. So here's a combination of a 3D image of the nucleus of the comet showing the jets in 3D. And one of the remarkable findings was that the jets, there are at least 2 of them on the dark side. Now, the reason the gases come out of comets is because of sunlight landing on the comet, heating up the surface. The comet's actually black, and even though we're way out in the outer part of the solar system now, the surface of the black surface facing the sun is actually about room temperature. Below the surface, it's extremely cold, but the surface is actually warm. But the backside in the shadow, you would think it would be cold and wouldn't be active, but apparently it's retained heat. It's spinning around an axis about in the middle of this picture, and it's retained enough heat down there that 2 of those jets, the upper one we call Walker, and the lower one on the lower right squirting out in the back is called the alpha jet. So these are actually squirting off in the dark. That was a huge surprise. Okay, this is non-stereo now, so you can put the stereo glasses away. This is the sample return capsule. This is what brought our collected samples back to Earth. The picture up on the upper right is a high-speed test of the thermal protection material that brown stuff on the bottom end of the sample return capsule. That's the ablator material. It's about 2 inches thick. That's what protects the capsule from being incinerated at coming in the atmosphere at almost 29,000 miles an hour. You can see on the bottom we had a world record entry speed. Now normally it's great to set a world record, but not something like this. So there was a fair amount of concern. No one had flown this material, it's called PICA, phenolic impregnated carbon ablator, before. It was a lightweight stuff, and the people at NASA Ames had developed claims that we could not have done this mission without this special ablating material. But nonetheless, this was the first test flight. And so there was concern about them. This probe on the upper right is how they tested. It's really kind of interesting. They have this wind tunnel, which they put about 50 megawatts of power into for like 45 minutes, and it's like a lightning bolt into this stream, and you get this jet flying out, and you have this test model on the end of a copper pipe, and you just push a lever. It's built in the 50s, and it just flips into the airstream and starts burning up. It's really pretty neat. It's a great facility if you ever want to test extreme heat effects on some sample somewhere. Now, so we were worried about the heat shield, but there were also other things to worry about, lots of things to worry about. The worries all diminished as we got further and further through the mission and got more things behind you. But I want to mention two other things that could have gone wrong. And one is that the parachute might not have come out. And this is a picture of the Genesis spacecraft, which collected samples of the sun, solar wind, and re-entered the same place we did about a year and a half earlier.
Vertigo Mach, it looks like we have a no-shoot, sir. Vector 200,
Mission
put it on your
manager,
nose, 8 miles, look for an impact.
SBC, negative stroke, negative shoot.
Copy, we see the visual.
Impact at 5855 past the
We
hour.
have an impact.
Impacted vehicle on the surface.
200 miles an hour impact. Actually, a lot of the science survived from that, but this was something that we were worried about because of the crash of Genesis and because of the Columbia shuttle explosion. We were put through unimaginable torture over the last year of the mission to assure that we would not that we would have a maximum likelihood of not making a mistake and coming back and landing on Earth. So no matter how careful you are, and everything else on Genesis worked perfectly, but no matter how careful you are, there's always a possibility that there was some slip up somewhere. And what got Genesis happened before launch. There was a mistake made on the G switch. It's the same kind of, generically the same kind of switches that pop out your airbags in your car. The G switch was put in backwards, and it wasn't caught. And fortunately, ours was put in right. Theirs was actually, we launched before them, and their design was based on ours, but somehow theirs got in backwards. We actually tested ours on a centrifuge. Another thing that could have gone wrong, lots of things can go wrong that are completely out of your control, and this is kind of an interesting one. When NASA would pound on us about reliability of this and that, I would often say, well, you know, comets are weird objects. Unlike anything else in the solar system, they come apart. They just, you know, they're heated by the sun and they just come apart. And each comet has about a 1% chance of just coming apart, disintegrating every time it goes around the sun. So I said, you know, before we worry about 99.9% probability of us being successful, the comet has about a 1% chance of not being there when we get there. Well, this is Comet Schwarzmann-Bachmann 3. See the date? April 20th, 2006, picture taken with Hubble, just this last week. This comet will be quite nicely visible in the coming 2 weeks. You can see it with binoculars, maybe even with a naked eye. This is a comet that's coming apart. See all those little dots up there, it's coming apart before your very eyes. Our students and people in the faculty are having great fun sort of watching this from different telescopes. The people on campus are watching. There's a class actually monitoring this with telescopes around the country. But just imagine what would have happened if we got to the comet just before we got it. It did this. I mean, what would we have done? We thought about, you try to think about everything. What would you do if this happened? Would you just go through the middle? Well, if you did, you'd probably get hit a rock and destroy the spacecraft. We actually had a shield on board on the front that would protect the spacecraft from the impact of a rock about the size of a grape. And the biggest rock we hit was about half the size of a grape. And if we would have flown through that, we probably would have hit something larger than a grape and wouldn't have survived. Even if we flew through again and the comet didn't come apart, we might have hit something bigger than a grape. You just really don't know. Anyway, here's where we're heading for. We landed in Utah at an area called the Utah Test and Training Range. That green thing in the upper right is the Great Salt Lake, and Salt Lake City is just to the right of that. The line across the top is Highway 80. The big circle is our landing ellipse. This is a fascinating place. The area just below the 7 is called Granite Mountain. And right above that, a thing called Wildcat Peak, and a little thing above that's called Kitty Cat. And we were sort of aiming between those things at the middle of the ellipse. If you get bored sometime, or you like to play around on the internet, go to TerraServer, Microsoft's program for looking at Earth from satellite images. And I just happened to put a piece of TerraServer image on here just for fun. This is one of the most fascinating places on the planet at high resolution as viewed from space. Utah Test and Training Range and Dugway Proving Ground has been used for testing of various sorts since World War II. They've done all kinds of, so there are all kinds of very strange things out there carved into the desert floor from various kinds of tests. It looks quite bizarre as viewed from space, all these concentric circles. Those concentric circles are about a couple miles across. It's a spectacularly beautiful area out there. And I would love to show lots of pictures of the pronghorn antelope and the deer and the mountains. But unfortunately, it's a secret site. They won't let me take my camera out there. So, but there's also a lot of people that believe the nasty U.S. government has captured alien spacecraft and keep them and the aliens locked up in this area. That's why. And actually, when you're out there at Utah Test and Training Range or Dugway, it is kind of funny because the people that work out there have these little alien creatures all over the place. It's not unlikely at all to look through a window and see, one of these heads, alien heads, stuck on a window, behind a window or something. Actually, when the press came in to look at our spacecraft after we landed, someone had put one of these things on a mock-up of it, just as a joke. Some people don't think it's a joke, but anyway, the reentry process was quite spectacular. We came in from the west at about an 8-degree angle, and even though we didn't fund this, there was a NASA-funded airplane that flew a crew out to observe it, and they observed it from just south of Wendover, Nevada. The Wendover is the place where the B-29 crews, the nuclear B-29 crews, trained during World War II. And they circled down there and got some quite interesting views and measurements of it. This was a great catch. We had a 100-pound capsule coming in at a known time, at a known place. This is a fantastic calibrator for various aspects of atmospheric entry and to study how the capsule survived. So this is a picture Brad Fisher took looking over Wendover of the fireball coming down. It looks like in the daytime. This is 3 o'clock in the morning. The sky was actually black. This is a time exposure. That's why you can see the clouds and so forth. Where I was at ground zero. So that's where the line is pointing to. So he was coming straight at us. Actually, he was climbing up in the sky. I'm an astronomer. This was the most spectacular thing I've ever seen in the sky. And people were literally screaming out there to see this thing. Normally when you see a meteor, a fireball in the sky, it's like a second or two, and it's like, wow, that was really cool. And you say, well, what did I see? But this lasted about 45 seconds. And it just got brighter and brighter, and there was this fantastic golden glow. And then behind it was this phenomenal gold afterglow. I mean, it looked like something from an old Disney movie where someone had a Stardust wand and went across the sky. And it was just really fantastic. I don't know actually how bright it went, but it was certainly brighter than Venus. And it was this golden color. The moon was up, so you can compare the color with the moon. The moon is ghostly white, and this thing was golden color. But here's a view from black and white, looking out the window of that airplane, at about 35,000 feet.
5, 4, 3, 2, 1. Pleiades, rapid brightening.
So you see the Pleiades up in the top there. It's halfway between
descent
Pleiades and the
season.
ground.
Near spec is acquired.
We see it.
17 degrees aft.
That's Mars next to the horizon down there.
Above Mars. Peak heating.
Oh, that's cool.
Foresight.
Quite a trail.
Near spec has a great view.
Air plasma lines have been detected.
That's the window of the airplane. So the Japanese film crew from NHK got a phenomenal high HD color video of that, which hopefully we'll have soon. Anyway, it was a thrilling thing to see. But even if it enters, now the entry process, we separated from the capsule, from the spacecraft, 4 hours before entry. That's about halfway to the moon, believe it or not. It took Apollo 3 days to get to the moon. It took us, about 8 hours to go that distance. We separated the capsule, and there's a really nice video showing that process from a telescope, Haleakala in Maui. You can see the dot, the Stardust, going across the background stars, and then all of a sudden it's 2 dots. And the capsule was coming on in. We actually diverted the spacecraft to keep it in space. So here's the capsule. The capsule came in, the parachute came out, both parachutes. The drogue parachute came out, the main parachute at 3 o'clock in the morning. It came down, it bounced on the desert, slightly muddy out there. It actually flipped around. It hit it at the nose, and it flipped on its side, and flipped around, and then it started rolling on the rim, and it went quite a ways, and then it fell on its side for a little bit, then it got back up and rolled like a drunken sailor a little bit, and finally got to the end and did this little pirouette at the end and stopped. And those shrouds coming out the back, that's what connected to the riser where the parachute was on, and that had a 10G switch on it, so as soon as it hit the ground, would explosively cut that off so that the parachute wouldn't drag it over to Nevada or something. So anyway, it was picked up and brought back to we had set up a clean room in case something had gone wrong at UTTR, and it was partially disassembled there. And then we took it back to Houston. This was our first look. This is Mike Zielinski and I in the clean room at Johnson Space Center, having the first look at the collector after 7 years. We're actually looking at the back side of the collector. The front side that faced the comet is facing down. And so we kind of looked worried there. We were looking hard, but after a little while, we started seeing impacts looking all the way through this thing. This is about 4 centimeters thick. And we saw 6 of them looking from the back side. Then we looked from the front side. It was just fantastic. So all day long, we were just beside ourselves with joy. And the reason we were so excited was these little particles, which I had warned people that these are small particles. We might not find any impacts with the naked eye. We might have to use microscopes. It might take a couple of days. And yet, as soon as we turned it, flipped it up, we could see them. Those are impacts. You see those big marks on the side? There's about 8 impacts here you can just see with the naked eye. The biggest one on the far right is called Big Bertha. The next one to the left of it, it has no name. It's a little bit smaller, but it's big enough that you could stick your little finger in if you wanted to. Well, even if you wanted to, you couldn't do it. You'd probably get shot by someone. So after the first day, we had to every night we take this and put it in a special gas flow controlled system, so if the fire extinguishers come on accidentally or something, it doesn't get wet. And so some people took turns seeing what felt like to hold $200 million in their hands. So that's the ice cube tray. Okay, so here's what the ice cube tiles look like. And those are impacts circled there. Now what was truly astounding was that the biggest impacts you could easily see from 30 or 40 feet away. So that carrot-shaped thing in there is an impact. Particle came down, hit, made this big bead-shaped thing, and particles survived at the end. Every single impact has visible material at the bottom, which is just great. We were really worried that comet particles might not be capturable very well by this technique. So aerogel is a weird material, and we've learned to live with its bad properties and take advantage of its good properties, and really cool techniques to deal with it. This is a technique called keystoning, which was developed by Andrew Westphal at the University of California, Berkeley. They take little computer-controlled needles and plug out a little triangular plug that has the track in it of the impact. It's kind of like taking a toothpick and going around for a couple hours, poking a hole in a watermelon until you get a wedge, and then pulling out the wedge. So here it's pulled out. It's pulled out on a little silicon pickle fork that are custom made. So that's a pickle fork holding on the right. So that's the wedge of aerogel, glass. And that's the track going down it. It's amazing. So here's this kind of thing blown up. So this is the track. Particles entered on the right at 6 kilometers per second. Slowed down and pieces of it stopped to the left, and you see blow-ups of it here. Here's just some pictures. There's two twin ones who are just amazingly similar and very close to each other. Very, very odd. Here's another one. This is actually a famous particle, but that's a track, and there are individual particles. There are actually thousands of particles in there. Those are just the bigger ones that are in the pictures. Just some more. Here's a particle that missed the aerogel. It hit the aluminum frame that held the aerogel, made that black thing at the bottom as an impact crater in the aluminum, and the debris went up, shooting upwards into the aerogel. You can see this radiating thing is going away from the explosion. That's an experiment that if you tried to do, it would drive you nuts to try to do at this scale. So how do we analyze these things? There are 200 people around the world right now during what we call a preliminary examination phase studying these samples. We use techniques like this. That's an atomic resolution microscope, which can resolve spatial distances equal to the size of an atom. The instrument on the bottom is a mass spectrometer, which actually didn't exist 10 years ago when we were funded to do this project. It's a mass spectrometer which measures the isotopic composition on grains less than 1/millionth of a meter in size. The big gizmo up on the left, it's called a synchrotron. It has relativistic electrons that are circulating in that big circle, and they generate X-rays and ultraviolet and infrared that can be focused down in really tiny spots to analyze the samples. And one of the ironies is to do the finest analysis on the small scale, sometimes you need the biggest instruments. So you can look in the far right-hand corner of that thing, as like a little rectangle. That's the parking lot. So you would never dream, not in 10,000 years, of putting an instrument like this on a spacecraft and sending it somewhere else to do the kind of things that it can do. And even if you could get something like that, you couldn't afford the service contract to keep it working in space, or keep the staff required to replace the light bulbs, et cetera, and clean the floor and so forth. So here's some of the tracks. I'll just show you a couple of things we do. This is tomography to get at using X-rays from a synchrotron to get at the geometry of the tracks. Here's composition with a synchrotron beam, X-ray beam. You can actually map that blue thing in the middle of the picture is a track imaged in iron X-rays. And you can see that the terminal particle, the particle at the end of the track, contains most of the iron in the sample. And the wiggles on the bottom is a spectrum that tells us the composition of the particles. You can different elements there. You can see calcium and chromium, manganese, iron, nickel, germanium, arsenic, selenium, bromine, and so forth. It's amazing how you can do this. So another irony of this, the particles we're working on are small. They're microscopic. But they're much too big for us to do a lot of things we have to do. So to get a typical size particle, we often have to take it and slice it up into hundreds of slices. And we like to slice it up into slices that are like a few hundred atoms thick. We need to do this to do electron microscopy. So these are two instruments used for slicing. One at the top is a diamond microtome. Uses a very sharp diamond knife to slice slices off. Biologists use all the time to do this for tissues and so forth. But we're cutting rocks. So a little interesting technology developed to do that. The instrument on the right is called a FIB, Focused Ion Beam Instrument. It's actually developed, made down in Oregon. And it uses ion beams and just basically take a rock and slice it up into slices like bread. And it can do this on very small scales. It's amazing. The FIB, the Focused Ion Beam, is heavily used in the electronics industry to study defects and problems with semiconductors and the actual character of the semiconductors as they're manufactured, as they're made. So what's comet dust look like? Here's some pictures of comet dust in the microscope. The earlier pictures were little particles you showed in optical wavelengths. This is the electron microscope, which is much higher magnification. The dark and light things in here are minerals. There's silicate minerals, and the gray material in between it is glass. And there's been a lot of scientific discussion about glass and minerals in comets. Well, we have the material in hand and can study it in excruciating detail now because we actually physically have these samples. Now here's a sample. This is a crystal of olivine, a famous mineral that makes up the green beach sands in Hawaii. It's a magnesium silicate, almost pure magnesium silicon and oxygen. It has a rim of melted aerogel around the outside, and that gray stuff way around the outside is just aerogel that hasn't been affected at all. But this particular mineral is interesting because in the early solar system, it takes tremendously high temperatures to form this. When this mineral formed, it was glowing white hot. And here's a close-up of it. Here's the mineral grain is on the bottom. It's called forsterite. Around it, on the middle of the image is a thin rim of where it interacted with the aerogel, and on top is unmelted aerogel. So we identify the mineral. We measure trace elements like calcium and manganese and aluminum in it. And we'll also be measuring the isotopic composition soon, and those provide really important fingerprints that tell us about what kind of environments could have made them. And frankly, so far these minerals are unusual for extraterrestrial materials, exotic. And I think they're going to tell us a lot. This was the second particle we worked on here on campus. And this is a particle, it's broken up during the cutting process. That's why it looks so ratty. But the mineralogy is amazing. There's 7 different minerals in this tiny little slice of sample. This slice is only less than 1,000 atoms thick. But we put an electron microscope, we put the beam on it, and we can determine the mineralogy and composition at very, very fine scales. We identified minerals with names like anorthite, spinel, diopside, and even vanadium and titanium nitride. This is really exciting because these are considered refractory minerals that form at extremely high temperatures, the highest temperatures that it could have possibly existed in the early solar system. And this is amazing because here we went to the edge of the solar system, the coldest, most distant place, and we found the hottest possible things. They weren't hot when we collected them. They were hot when they formed. So they're fantastic clues. They're just different ways that we actually use to study these things. There are lots of weird minerals that we found. We didn't expect to be so surprised. We were actually overwhelmed with the phenomenal things that we've been finding so far. We believe we have found things from the inner part of the solar system that form very close to the sun. And also, we're pretty sure we've found particles that are older than the solar system and are formed around other stars. So we also can work on craters and analyze the materials in craters. But the overreaching thing is that here we went, we sampled a comet that formed at the edge of the solar system. We found the hottest minerals in the coldest place. How did they get there? We will definitely be able to tell you, in like a year or so time. A lot of people working on this, and it's just absolutely thrilling and fabulous to have these samples. There's nothing like having samples. You can pretend, you can wish, you can make up all kinds of stories, but when you have the library to work with, it's the difference between a night and day. And this sample is essentially our library, the secrets, we think, of certain aspects of the solar system are there. So I have a little video here to summarize the mission.
January 18, 2006. From Comedy Central's World News headquarters in New York, this is The Daily Show with Jon Stewart.
Welcome back to the program. It's time once again for our wildly popular recurring segment. Holy all right. On Sunday, the Stardust space capsule landed safely in the Utah desert, capping a 7-year journey with a smooth descent, seen here in the first night vision footage ever shot not featuring sex or something blowing up. The capsule bore precious cargo, a thimbleful of particles gathered from the tail of a comet. Comets, of course, frozen bodies of ice and dust formed over 4.6 billion years ago, or created 6,000 years ago, depending on whether or not you're wrong. The spacecraft wound up landing in mud at the Army's Dugway Proving Ground. From there, it was delivered to a nearby room for sanitary inspection by excited astronomers.
Wow, looks a lot smaller than I remember it. I was just about to say that. It's way smaller. I guess over the years you kind of build it up in your mind. Totally. It looks way smaller.
Yesterday, seemed like a banal conversation to record, but that's the way it goes. Yesterday, the capsule was flown to the Johnson Space Center in Houston, where scientists unlocked the canister, and with it, a tiny, precious amount of cosmic material that may very well contain the secrets of the solar system. I believe we have footage of that thrilling moment. We'll be right back.
So anyway, so thank you very much. And